Hi friends, let's begin by understanding how Spark actually works behind the scenes. At a high level, Apache Spark processes large dataset by distributing work across many machines in a cluster. Instead of relying on a single powerful computer, Spark breaks a job into many smaller tasks and runs them simultaneously across multiple nodes. A better way to visualize this is in two parts of the systems. The one is the brain and the other one is the brain represents the application logic, the intelligence that decides what computations to happen. The body represents the physical missions that actually perform them. At the center of the brain is the driver program, often called as a Spark driver. This driver is responsible for reading the user's code and translating it into a sequence of operations that Spark can execute. When a Spark program starts, the driver analyzes the operations written by the developer and converts them into a directed acyclic graph, commonly known as DAG. This DAG represents the logical flow of computations, essentially the roadmap showing how data transmission depends on each other. Once the DAG is created, Spark divides the work into stages, and each stage is further split into many smaller tasks. This task represents the smallest unit of work that Spark can distribute across the cluster. The driver then begins task distribution, sending these tasks to different in the cluster so they can run in parallel. This parallel execution is what allows Spark to process extremely large datasets very. On the infrastructure side, these tasks run inside executors, which are processes running on worker machines. Each executor has access to computing resources such as CPU cores. Inside each executor, multiple tasks can run simultaneously using threads. The executor also maintains a memory area known JVM heap where intermediate data and cache datasets can be stored. One of the major reasons Spark performs so efficiently is its in-memory computing capability. Instead of repeatedly reading and writing data to disk, Spark can store intermediately results directly in the memory. This makes Spark particularly powerful for workloads like machine learning, streaming analytics, interactive algorithms. So, in summary, Spark works by transforming user code into DAG, dividing the work into tasks, distributing these tasks across multiple machines, and executing them in parallel using the executors that leverage in memory processing. Moving on to the core Spark architecture, there are few components that make Spark capable of distributing. The architecture of Apache Spark is designed with a clear separation between application management and infrastructure management. This separation allows Spark applications to run efficiently while underlying cluster resources are managed. At the top of the architecture is the application driver, which acts as the control center for Spark application. The driver is responsible for building the execution plan, scheduling tasks, and coordinating communicating between the different components of the system. While the driver manages the logic of the application, Spark relies on the cluster to handle the physical resources available. The cluster manager is responsible for allocating CPU cores memory to Spark based on availability. Spark can work with several cluster managers including Apache, Hadoop, and Kubernetes and its own standalone cluster. Within each machine, resources are allocated using containers. Containers provide isolation between different applications, ensuring that each job receives its own dedicated portion of CPUs and memory. This prevents a single application from monopolizing the cluster resources. Inside these containers, Spark launches executors, which is responsible for executing tasks. Executors run as a Java virtual machine processor, allowing them to execute multiple tasks in parallel in threads. As tasks are executed, executors can cache intermediate results in their memory. This cached data can then be reused by later stages of the computations without recomputing it, which significantly improves performance. Another important aspect of Spark's architecture is its fault tolerance. If a task fails due to the node failure or network issue, Spark can automatically re-execute that task on another executor using the lineage information stored in it. This ensures reliable processing even in the large distributed cluster. Overall, the Spark architecture ensures that applications can run efficiently, scale easily, and recover from failures without manual intervention. Finally, let's look at the Spark cluster master and worker node. A Spark cluster is made up of multiple machines working. These machines are divided into two main roles, master nodes and worker node. The master node acts as the central coordinator of the cluster. Its job is to manage the overall state of the system, allocate resources to running applications. The master node communicates with the cluster manager to determine how many resources are available, which worker node can run execute. It also monitors the health of the cluster by receiving periodic heartbeat signals from worker nodes. When a new worker node joins the cluster, it registers itself with the master node. The master then keeps a track of the available CPU memory across the entire cluster. The worker nodes, on the other hand, are the machines that perform the actual computation. Each worker node provides hardware such as processor and memory that Spark uses to execute tasks. Within each worker node, Spark launches executors inside containers. These executors receive tasks from the driver and execute them using local resources of the machine. And the tasks are completed, the results are sent back to the driver. The driver then combines these results, produces the final output of the Spark. This distributed model allows Spark to scale from just a few machines to thousands of servers, enabling it to process extremely large datasets efficiently. By distributing tasks across worker nodes and coordinating them to master node, the driver program, Spark achieves both massive parallelism and high fault tolerance. And to summarize this, Apache Spark is designed around a powerful distributed computing model. First, the driver converts the user code into DAG and distributes the task across the cluster. Next, the core architecture manages how applications interact with resources, and finally, the cluster infrastructure consisting of master and worker node provides the physical environment where all the computations takes place. This layered architecture is what allows Spark to process massive datasets quickly, scale across large clusters, and deliver reliable performance for modern data analytical workload. Thank you for watching. Catch up in the next video. Until then, take care. Bye bye.